I love the topic of moments. It's just a beautiful thing. It is a beautiful thing to talk about it, and I could talk about it all day. I'm sure that my friends are all sick of me talking about moments. But okay, so what's going on here is there is one math formula that explains a lot of different things in a lot of different contexts. So what do you do when something like that happens? What you do is you learn the interpretation of those formulas that makes physical sense. You learn the interpretation of them that you can feel and hold and touch and imagine if it was a real physical object in front of you. And then when you have to solve another problem, maybe it's about probability or statistics or electric force or something, you can interpret the meaning of that object in terms of the thing that you already understand. Okay, I put here the little portrait of Archimedes of Syracuse, and you can see he was alive in he was born in 287 BC, so more than 2,300 years ago. So we've been aware of this information for a long time now. Right, so what are the important things that he contributed? One of them is this. It's called the law of the lever. Basically, if you have like a teeter-totter or a seesaw or something, and you put a mass on the end, then the force that is generated by pushing down on that is proportional to the length of the lever arm multiplied by how much mass it is. So twice the length, twice the force. Also, I put here the formula for rotational inertia. This is the amount of energy that is stored in a rotating object, or equivalently, the amount of energy that it would take to cause an object to rotate. So it's proportional to the square of the length of the arm. So we call it the moment arm, the square of the moment arm. So just imagine, imagine having a rock on a string and spinning that above your head. And what you're going to do is try to keep the RPMs the same. So just imagine if you like doubled the length of the string. I mean, the string would be much longer. And I think if you imagine it, you realize it would take a lot more energy in order to keep the object, the rock, rotating with the same RPMs. In fact, if you doubled the length of the arm, then it would be exactly 4 times as much energy stored in the rotating object. If you tripled the length of the arm, it would be 9 times the energy stored in the object. Okay, so all of these things, the moments, the mass, the center of mass, and the rotational inertia, all of them are based on these 2 properties right here. So let me try to break down what each of them represents. Suppose that you have some masses and they're all distributed on a line. And I've named all the masses M, and I've named their location X. So maybe this one right here is like M number 1 and its location is like X number 1. And then over here, maybe this is like mass number 7 and its location is like X number 7. This one was X1 there. All right, so if you have a bunch of masses and they're all distributed on a line and you add up all of those masses, what are you going to get? You're going to get the total mass. Okay, so I'm going to skip this one for a second. We'll come back to that one in a minute. But let's look at this one right here. So what are you going to get if you do x squared times the mass? Then each one of these little things is going to be the amount of rotational inertia stored in each little piece. And then if you add them all up, you're going to get the total rotational inertia. And I've drawn a little like tightrope walker guy here. And this kind of makes sense. Tightrope walkers, they hold these like rods and then they put masses out at the ends of the rods. And this is to make their rotational inertia as large as possible. I think it makes sense that if you were going to be like a tightrope walker, you would want to not rotate very much, right? Because you're trying to balance. So they do this so that they have a very large rotational inertia. Okay, so let's try to unpack this one a little bit. The mass times the center of mass. This is important. This is a big part of probability and statistics. And before we do, I just want to point out the pattern here in case it isn't obvious. The 0th moment, that is really x to the power of 0. And then the first moment you can see right there, x to the power of 1. And then the second moment you can see x to the power of 2. And you can go on. You can go on. You could do x to the power of 3 times all the masses, x to the power of 4 times all the masses. And the idea, the use of this word moments, originally what they were trying to communicate is that these are important properties. Anytime you have some kind of physical object, all of these calculations represent important properties. And I want to look now here at the first moment. We like to use x bar to be the center of balance. The idea is that's where this kind of teeter-totter shape would balance. I kind of eyeballed it. I just put it right here. All right, so mi is mass 7 or mass 13 or whatever this mass is, and then its distance, its location is xi. So the distance between the center of balance and this ith mass, the 12th mass or 13th mass or whatever, is going to be the difference of them. And then I used the law of the lever to figure out the amount of force that would be pulling on the center of mass due to this little piece over here. Then the assumption is that x bar is supposed to be the balance point. So what that means is that all of the forces balance out. The forces on the left, plus the forces on the right, you're all going to get 0 there. That's what it means for it to balance. So that's what I wrote down here, what it means for all the forces to balance. And then the rest of this is just like arithmetic, right? I mean, I just distributed this mass number I to both pieces, and I used associativity to recollect the terms, and I moved them all over here to the other side. Then x bar is a constant, so you can see I just factored that x bar out. And then that let me solve here for x bar. So this is the derivation of where you get the center of mass. You take the total mass, you add up all the forces, and then you divide that by the total mass. So hopefully this is kind of starting to look like an average location of all the masses to you. Okay, so that's it. We have all of these beautiful things, all of these moments, all of these important properties. The 0th moment is what you get if you add up all the mass. That's the total mass. The first moment, if you rescale that down by the total mass, then that gives you the center of mass. And then the second moment here is the rotational inertia. That's how much energy is stored in the object if it is rotating. Okay, so that's the theory. These are beautiful things. Thank you, Archimedes, for kind of assembling all these pieces for us. Let's do some Calc 3 level classroom examples of finding the moments. This always drives me nuts that they make up a new word for this, a centroid. I guess that's what they call a center of mass if it has constant density and the density is 1. So I'm sorry for that language. I don't feel like we need another name for this. But if you ever see a centroid, that's what they mean. They just mean center of mass. Okay, so I've cooked up an example here where we can do the whole thing. So what we're asked to do is find the total mass, the center of mass, and the moment of inertia. And I give us a thin plate, and this thin plate has variable density x squared plus y squared. So this is actually radial density. So this is going to be kind of not very dense here in the middle. And then as we go out, it's going to get more and more dense. And then out here, it's going to be like really dense. So I don't know. I don't want to draw it. Yeah, so that's the setup. And let's see if we can figure out the total mass of this. All right, so what I'm going to do is I'm just going to imagine some small little piece there, and I'm going to call that piece dA. And then the change in mass, I'm going to call that dm, is just going to be the density multiplied by the size of that little piece because it's a thin plate. I'm imagining the thickness of the plate to be 1 unit. Okay, so that's it. So that is the mass of one small piece. So the total mass is going to be what you get if you just add up all those little masses. So this is what we've been doing with double and triple integrals the whole time. So that's what I've got set up here. My limits of integration for this problem are going to be 0 up to, so I solved this for y. I chose to do dy first. So what, -2/3 x plus 2, and then that's going to be valid for all the x's are going to be in between 0 and 3 there. All right, so let me work this out. Okay, so let's move on to the center of mass. I always forget this. You got to start by rescaling the mass down by, or rescaling the calculation down by the total mass. Okay, so 1 over the total mass. And then what I'm trying to do is just this one-dimensional formula where I do the location of a piece of mass multiplied by the amount of mass that is there. So I'm going to need to add all these things up. All right, so if I consider like a little piece of mass, a little piece of area right there, then just as before, the change in mass, the amount of mass in that one little small piece is just going to be delta times dA. Except what I want to do is figure out how much force is going to cause this thing to move, to like tip to the left or tip to the right. So that's going to be this distance right there, x. You can see like if the center of mass ends up being like right here or something, if that's where the x bar is, then that little distance right there would cause it to rotate in that direction. All right, so this really is, like from the student point of view, it really is just this simple. You just put an x in front of it. Okay, so that's one of the things that I like about this is that it really is just like a beautifully simple calculation to do. Just don't forget to put this 1 over the total mass out front. I'm an idiot and I always forget it. All right, so one more quick little thing about this. You can see what we're actually calculating when we do this is, this would cause this object to kind of, you can see sort of rotate in that direction there. You can see it would kind of cause it to all fall like into the page. It's going like into the page this way. Doing my best to draw these arrows. So because of that, sometimes you will see textbooks call this thing m sub y, because that, that is how much force is pushing it around the y-axis. In my mind, we don't need to bring like extra symbols into this. It just really is that easy. When you're trying to figure out the x center of mass, you just do the same thing as the first moment and you stick an x in front of it. But if you do see that, sometimes you will see this called m sub y. I don't know, that's just a little bit confusing to me. I don't think we need another name for that. So let me set up the y bar. I think you'll see it is equally as simple. So there really is nothing to it here. When you're looking for the y center of mass, all you need to do is just slap a y in there. And then, just like before, you'll see some textbooks call this m sub x. This is the amount of force that would cause the object to rotate that way around the x-axis. So they'll call it m sub x. Okay, so there it is. This is how we calculate the center of mass of two objects. I'm not really too concerned. I trust you guys to be able to work out these double integrals. So now let's move on to figuring out the second moment. Here we have the 0th moment, and then both of these things right here are the first moment. And now let's figure out the second moment. Okay, so these last two calculations, the limits of integration of these things are all the same. So you're going to see this, the moment about the x-axis, this is going to be the amount of rotational inertia that something has if you revolved it around the x-axis. So let's just look and see where our little mass would be. So if we're trying to rotate this around the x-axis, it's rotating this way. Then the moment arm is actually going to be the y distance. So I understand that this is a little bit confusing, but it does make sense. If you are rotating something around the x-axis, then the radius is going to be y squared right there. So, here is one full complete setup of all of the different moments. Basically, you just integrate the density, and then, then you don't forget to do that 1 over m, and then you integrate the density again with an x in front of it or a y in front of it, and then you integrate the density again with an x squared in front of it or a y squared in front of it. So, kind of the beauty of these problems is the simplicity with which we set these things up, and sort of how we can take all of these different important physical properties and kind of boil them down to one really simple formula. So, this probably is maybe an overly simple example. You know, maybe you might run into some problems that are a little bit more difficult than this. So please, you know, if you have some difficult problems, you know, reach out to me and let me know, and I'll see if I can give you a little hint.